Okay, everybody. So here's going to be me tidying up what is left of Chapter 8 that I'm going to cover. So the last few sections of Chapter 8 give you some specific examples, and I'll talk about those and I'll refer to those later as far as examples go. But the main bulk of what we want to talk about is in the first two sections. So in class last Friday, I had started on 8.1. So I had defined Gaussian and mean curvature, and I had computed this corollary, or as this corollary from last time. I finished proving this, that the mean curvature, h, which we're not going to talk about nearly as much. It's a kind of a more complicated quantity. I'll mention some things about the mean curvature before the course is over and point you in the direction if you are interested in more of that kind of stuff later. Here was the mean curvature. So E, F, G, L, M, N are as usual from first and second fundamental forms. And the Gaussian curvature K is Ln minus m squared over Eg minus f squared. Now, I mentioned, while this is our first and kind of our one of our better formulations of or form that the Gaussian curvature is going to take, and this definitely seems to depend on both the first and second fundamental form, it's going to turn out that we actually don't need the L, N, and M here. We can actually do this referring only to the E, G, and F. So this is an amazing thing here. Okay, now to it'll be a little bit before we get to that point, but this is where we are now. That the mean and Gaussian curvature can actually be written in this way. So this is the last thing I proved last Friday. So I want to do an example where I actually compute the Gaussian curvature for a class of surfaces. So our favorite class of surfaces are surfaces of revolution. And so if I want to apply this to surfaces of revolution, let's say I have my usual surface of revolution given to me by surface patch. So locally it looks like f of u cosine v, f of u sine v, g of u, where the profile curve f of u 0, g of u is unit speed, and we assume that f is positive, so f's positive. The profile curve is unit speed, which we know leads us to say that f dot squared plus g dot squared is equal to 1. So this is the usual assumption we're working on, and this is true everywhere. Again, this is the assumption that the profile curve is unit speed. Okay. Now, we have already worked out E, F, G, L, M, and N from previous examples. So from prior examples, E was found to be 1, F 0, and G was found to be F squared. Right? L was computed to be F dot. So dot here denotes derivative with respect to U. So L was found to be F dot G double dot minus F double dot G dot. Okay, M is 0, and N is F times G dot. Okay, so we had previously computed all of these things. So now it just means we want to put this together to write our curvature here. So K is L n minus m squared over Eg minus f squared. Okay, so this is equal to what? Just putting this directly in here, L times n. This is, so m is 0, f is 0, so these terms go away. So this is just Ln over Eg. So this is f dot g double dot minus f double dot g dot times f g dot divided by E times g, which is f squared. Okay. Now let's make this a little nicer. So if I look at this, I want to think of a way of writing this algebraically to maybe be a little nicer, use some of these facts that I have. So for instance, I have this, right? So f dot squared plus g dot squared is equal to 1. What does that tell me? Well, that tells me, for instance, that f double dot plus g double dot is equal to 0, which tells me that, for instance, g dot times g double dot is equal to minus f double dot. How does this help me? Well, if I distribute this g dot here, I get g dot squared in this term, and I get g double dot here, which is minus f double dot. So I'm going to get an f dot squared, g dot squared here, f double dot in both terms. Algebraically, that's going to be something that's nice. So what do I get out of that? Well, this becomes here, like, this becomes like minus, how do I want to, I want to turn this into, this is going to be minus f dot squared times f double dot in the first term, minus f double dot g dot squared times f all over f squared. But then I have an f double dot in both terms, and I have minus f dot squared minus g dot squared. So I have minus, if I factor out a minus f double dot, this is minus f double dot f times f dot squared plus g dot squared all over f squared. Or simplifying, since this is 1, right, so this is 1, f cancels with f squared here, so what I get is minus f double dot over f. Okay. Now I'm going to rewrite that on the next page because we're going to use this to immediately compute Gaussian curvature for a number of surfaces. So this is my Gaussian curvature for a surface of revolution is minus f double dot over f everywhere. So let's look at some special cases. So what are special cases here? Well, first special case, what if I take my profile curve gamma of u to be just u 0 0 here? Right. So this is my profile curve, so this is just the x-axis. Then this surface of revolution is just the xy plane, so corresponding surface is the xy plane. F of u is equal to u. All right, so what does that mean? It means that f dot is 1, which means that f double dot is 0. So Gaussian curvature of the plane is 0 everywhere. That, of course, should sort of mesh with what I expect it to, right? If this thing is some notion of curvature, then I would hope that the Gaussian or the curvature of the plane would be 0 here. It would be, an uncurved, a not at all curved thing. Okay. But of course, there are competing notions of curvature here for surfaces. It's a little more complicated. So I have to be careful about, the sorts of reasoning I do here. But this is a good sign for us. All right. What about another special case? So what if I take my profile curve to be, say, 1, 0, u? Okay, what is the corresponding surface here? Corresponding surface is cylinder. In fact, it's the unit cylinder. Okay, f of u is 1, which means that f dot is 0. So, of course, f double dot is 0, which means that the Gaussian curvature of the unit cylinder is 0. Okay. All right. Now it turns out, I'm not going to do this here, but you can do this if you want. It turns out that if you were to compute the mean curvature of the unit cylinder, you will find that they differ. Okay, they differ. So maybe exercise, compute mean curvature of cylinder and compare to mean curvature of plane. So the Gaussian curvature of the plane and the cylinder are actually the same. You will see if you actually compute the mean curvature from the surface of revolution definition and actually computing, what this thing is just from our corollary even. Right, so using this fact, you will see that the mean curvature of the plane is 0, but the mean curvature of the cylinder is 1/2 or minus 1/2. Okay, and so their mean curvatures are different, but their Gaussian curvature matches up. There's a reason for that, and I've hinted at that in class, but we'll talk about that a little later. Another special case, what if the profile curve is, say, cosine u, 0, sine u? Okay. Well, this is a circle of radius 1. If I rotate this thing out, right, what do I get here? I get sphere. I get unit sphere, right? Corresponding surface is unit sphere. Okay, so corresponding surface is unit sphere. F of u is cosine u. So, of course, f dot is minus sine u, and so f double dot is minus cosine u. So the Gaussian curvature, which is minus f double dot over f, is minus cosine u over cosine u, which is 1. Okay. All right. Okay. So there's a little modification that can be done. Of course, you can do a modification here for this curve to to give you, say, the curve you pick would not be a circle of radius 1. You could make the radius whatever you wanted to. Parameterize that as a unit speed curve, you could get a sphere of whatever radius you wanted to. And then, my question to you is, what is the Gaussian curvature? How does this change? You might be able to answer that already. Okay. But here, we have that the Gaussian curvature for the unit sphere is 1 everywhere, at all points. Okay. Let's do an example, or I won't do it. I will relegate it to having you look at it in the textbook. But here's another example. Ruled surfaces. So in the textbook, there's a quick computation that's done that will show you every ruled surface has Gaussian curvature that is less than or equal to 0. Okay, everywhere. So this is page 182 in the textbook, I believe. Okay. So this is like your fundamental kind of building block for your intuition for what the Gaussian curvature is saying, but it won't become entirely clear until we've talked about some other things. So when we talk about principal curvatures, then it actually becomes kind of a little more intuitive as to what exactly the Gaussian curvature is computing at a point. Okay. Now, Gauss actually did not originally compute Gaussian curvature in this way. This came a little bit later. So Gauss's, I believe this is the original method for doing this. So Gauss's original method for computing the Gaussian curvature was as follows. He actually came up with a way to obtain the Gaussian curvature from the Gauss map itself rather than the Weingart map. So Gauss used the Gauss map itself rather than the Weingart map. Now, intuitively, what he did was basically the same thing, but there is a nice reason conceptually why Gauss's formulation should still be mentioned here. So, because what Gauss gets is an analog of this turning angle business. So, what he computed is an analog of our turning angle computations for curves. So the basic idea here being that just as we were able to define signed curvature, and we were ultimately able to say that sine curvature was the rate of change of the turning angle, right? So the turning angle kept track of how quickly a curve was turning. So if I have this thing, right, the turning angle was a measurement, right? Every tangent vector here to curve was being tracked by the turning angle. So the rate of change of the turning angle was telling you something about how rapidly a curve was turning, which of course is telling you something about curvature, okay, or what we understand to be curvature. And so the idea is to do that, except for surfaces, okay? So then what's the idea here? I have surface. The idea is that locally for surface, if I now think of these tangent planes being all over the place here, here's on the front side. Now, of course, like rather than just having a one-dimensional tangent object, right, the tangent line or tangent vector here, I have these tangent planes all over this surface. Okay, now while these are planes rather than one-dimensional spaces, I can keep track in some sense of the direction of the tangent plane, of course, by still a single vector, which is the vector that's normal, right? This is coming straight out of the page. So I can keep track of the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane in terms of the normal to it, right? So the direction of the tangent plane of the tangent plane to an oriented surface is measured by n. Okay. So we expect that the I mean, this was the reason why we used the Weingart map in the first place, was it was telling us something about direction. Since the Gauss map was tracking the normal, the rate of change of the Gauss map should tell us something about how this curve was curving, right? Because this was the rate of change of the direction of the tangent plane. So we're still kind of using this idea here with what I'm about to say, but it's slightly different. So we expect that not the measure, but a measure of the curvature of, let's say I'm dealing with a surface patch here for S, of sigma is the rate of change of the normal vector per unit area. Okay, so here's the slightly different thing. Before we just said rate of change of the normal vector, and we were happy to identify that quotation marked quantity with the Weingart map, which is the derivative of the Gauss map. Here, this is rate of change of the normal vector per unit area. Of course, the Gauss map records the values of the normal. So the Gauss map G records the values of the normal. Okay, and so if we're wanting to incorporate the rate of change per unit area or whatever, so if R or sigma of R, sometimes the R is what is the region in the, say, UV plane that we're mapping to, but we kind of identify these regions. So so if R is a small region on S containing, say, P, we look at this quantity, the area of the Gauss map of R over the area of R. And this will tell me something about the, I mean, this basically is measuring the rate of change of n per unit area, because it's taking Gauss map, applying it to every single point in some region. That should give me some region on the sphere. Okay, I compute the area of that, and I divide it by the area of R itself. Right? This should, in some sense, tell me this underlined quantity here, the rate of change of the normal per area, per unit area. Okay. And then what I want to look at, of course, is, you might say, wait, what does P have to do with this region? Because R is just a region containing P. The idea is that I look at this quantity, but really I look at a limit of this quantity as R shrinks to P. So I look at limit as R shrinks to P itself. Okay. Now, you, from your 2021 viewpoint, might say, oh, God, that this is already a more complicated and somehow nastier thing. So, keep in mind that limits were we didn't have epsilon delta for limits yet. That wasn't until Weierstrass that we had that notion. So things were a little squishier when it came to mathematicians pre-Weierstrass were a little more comfortable taking limits and dealing with infinitesimal quantities, and they weren't as caught up on some of the more kind of pathological things that can happen with with convergence, and so defining something in terms of this kind of thing is not necessarily it's not a red flag in any way. So let's see the actual theorem that Gauss showed that that associates this quantity to the Gaussian curvature. So here it is. Let sigma from U to R3 be a surface patch for S. We'll say let U naught V naught be point in U. You can think of that as corresponding to your point P on the surface. Let delta be positive such that R sub delta is defined to be the set of UV in the plane such that I should actually have just defined this as the set of, it's fine. So U minus U naught squared plus V minus V naught squared is less than or equal to delta squared. So delta is the radius of your unit disk centered at U naught V naught, and we're only concerned with when this is contained in U. Okay, and so we're typically thinking of delta as being very small here. Okay, then the limit as delta goes to 0 of A sub n of R sub delta divided by A sub sigma of R sub delta is equal to the absolute value of the Gaussian curvature, where these quantities A sub n R sub delta is the area, so this is the integral over R sub delta of the length of standard unit normal sub U cross standard unit normal sub V, du dv, and the area A sub sigma R sub delta is the similar computation using sigma here. So this is the surface area, if you like, right? The usual definition of area. So this is the integral over sigma sub U cross sigma sub V du dv. Yep. Okay. So these are your two integrals that compute the area of these regions, and it turns out that this limit is actually the absolute value of Gaussian curvature K. The proof is on page 183. I won't go through it here. The main thing I wanted to do is state this just to show you what Gauss was thinking when he actually derived this method of computing Gaussian curvature. And I want to note that actually this method of computing Gaussian curvature is superior to the explicit formulation we have in some cases, because in some cases we can actually compute this without any computation, which is nice. The other thing I want to note, you might complain and say, oh, this only gives me the absolute value of K and not K itself. But note, actually, if we define signed area, we can actually get K itself. So we can recover K itself by defining carefully signed area. So if we define signed area carefully enough, then the quantity that spits out of this limit is actually K and not absolute value of K. Okay, so this does it. You can actually do the Gaussian curvature this way entirely. Okay, the nice thing, we can use this to compute K without doing anything. So we can compute K in this way without computation many times. which is pretty cool. Okay. Why without computation? Because sometimes, in very specific cases, the image of the Gauss map is extremely simple, right? So maybe the surface in question is like not as simple, okay, but the image of the Gauss map is. Now, it is in general a very hard problem to consider, like for a kind of a generic surface, what does the Gauss map have to look like, right? Like, do I know in general, if I make a few assumptions, like what the image of the Gauss map has to be? There's a lot of very complicated questions that can be asked, not all of which have even been resolved, I don't think. So you can't make this nice generally, but in a lot of cases, for surfaces that are not even necessarily that simple, you can actually say, oh, well, the surface itself is not simple, but the image of its Gauss map is not that bad. So the image of its Gauss map is not that bad. Sometimes it makes this area thing really, really easy to compute. So for instance, let's do a couple of examples of this. Examples. Let's revisit the surfaces of revolution that we did previously. So let's do plane. Well, what do we know? Unit normal is constant. So the unit normal to the plane is constant. What does that mean? It means Gauss map. So Gauss map is a single point. Or I should say image of Gauss map is a single point. So G of R is equal to point for all R. Right? Well, the area of a point is 0. So Gaussian curvature is 0. No computation needed. Okay, let's do cylinder. Actually, let's do even better. Let's do generalized cylinder. Okay. So for a generalized cylinder, right? So before we actually just did unit cylinder, but now we're doing this for generalized cylinder here, which is an example of a ruled surface. So unit normal is not constant, but unit normal is always perpendicular to the rulings of the cylinder. Okay. What does that mean? This means, and you can think about this, Gauss map is contained in the great circle on unit. So this is contained in the great circle on unit sphere S2, such that, or I should say, formed by intersecting the unit sphere with a plane passing through its center perpendicular to the rulings. Maybe I'll just say it's contained in the great circle on unit sphere formed by intersection of plane that is so plane passing through its center perpendicular to rulings of cylinder. Well, the Gauss map is contained in great circle. Area of an entire great circle is still 0. So Gaussian curvature is 0. Again, no paper needed. You could have reasoned through that in your head. What about the unit sphere S2? Okay, well, unit normal is parallel to the radius let's say unit normal at P is parallel to radius vector pointing to P. Okay, we know it's parallel, right? Well, what that tells us is the Gauss map only has two options. It's either the identity, right? It's the unit vector that points directly toward P by the radius vector, or it's the antipodal map. It points in the opposite direction, right? This depends on orientation. All right, so depending on orientation here, it's either the identity or the antipodal map. So Gauss map is either the identity or the antipodal map. Those are the two things you could say. Okay, so this depends on your choice of orientation, which one it is. It doesn't matter, though, because both of these are equiareal. Now, we didn't do that much with equiareal maps other than define them, but both of these are equiareal. They do not alter area. Okay, since neither of them alter area, then what does that thing have to be? Well, when I say that thing, I mean this quotient. What does this have to be? Well, since the area is not changed, that quotient has to be 1. So I know that the absolute value of k is 1 from this. How do I actually get that the Gaussian curvature itself is 1? Well, if sigma is any surface patch of S2, then I know that the standard unit normal is either, plus or minus sigma, right? And so with either choice of sign, if I compute, say, n sub u cross n sub v, this is equal to sigma sub u cross sigma sub v. Okay, and this is a positive multiple of the standard unit vector, so I know that it actually has to be positive 1. Okay. All right. So this one wasn't quite as nice as the first two, but still, we were able to immediately get this pretty quick. Okay, and then we had to do a little bit more to get this. Like I said, we could do this. We could have done this in a way where we talked about signed area, and this would have been a little bit more straightforward here, but it's okay. All right. Okay. So that's nice. This is one particular way of thinking about the Gaussian curvature, or maybe a little bit about what the Gaussian curvature is saying for the surface. Okay. Now, I wanted to move on to something a little different, so that will hopefully kind of build your intuition a little more, because in some way, as we'll see when we get to the end of this, this description of a surface, or the Gaussian curvature of a surface, is going to let us explicitly say that near a point having some Gaussian curvature given in a certain form, we can think of locally that surface being approximated by surfaces that are maybe a little bit more familiar to us and more concrete. Okay, and so what I wanted to discuss is the principal curvatures of a surface. We will have a relation between these and some other versions of curvature on a surface that we've talked about before. Okay, so the principal curvatures are gifted to us from linear algebra, basically. Okay, and so the way that happens is the following. So recall that the Weingart map W is self-adjoint. okay, which comes with a whole host of really nice properties. Okay, so bilinear algebra, we'll say. If you're unfamiliar with any of these things, don't worry. I'm going to mention the stuff that's important that we get, but this is covered. Most of what you need is covered in the appendix, in the very first appendix in the textbook. So bilinear algebra, what do I get? So I have the following proposition. Like I said, I'm not going to prove this. This is spat out immediately from linear algebra. So let P be a point in S, then there exist scalars, say kappa sub 1 and kappa sub 2, and a basis that I'll call T sub 1 and T sub 2 of the tangent plane Tp of S such that W of T sub 1 is equal to kappa sub 1 of T sub 1, or times T sub 1, and W of T sub 2 is equal to kappa sub 2 times T sub 2. Okay. Moreover, if kappa sub 1 is not equal to kappa sub 2, so if this is not, you already see what these are. These are the eigenvalues, and the T sub 1, T sub 2 are the eigenvectors. But if these are actually distinct eigenvalues, then another fact you have from linear algebra is that the two vectors from differing eigenspaces are perpendicular. But for this case, we only have these two vectors. So then T sub 1 dotted with T sub 2 is 0. Okay. So, as I said, note, really what this is saying is that kappa sub 1 and kappa sub 2 are eigenvalues, and T sub 1 and T sub 2 are eigenvectors. Okay, that are associated with them, right? So T sub 1 is the eigenvector associated to eigenvalue kappa sub 1, and similarly for kappa sub 2 and T sub 2. Okay, so then our definition is at a point P, we call kappa sub 1 and kappa sub 2 the principal curvatures. We call kappa sub 1, kappa sub 2 the principal curvatures So these are the principal curvatures of S at P. Okay, and T sub 1 and T sub 2 are called principal tangent vectors, or just principal vectors. Corresponding to kappa sub 1 and kappa sub 2. Okay. All right. Now here is definition. We mentioned the possibility, of course, that kappa sub 1 and kappa sub 2 are equal at a point. All right, so if that's the case, right, this corresponds to having a repeated root of the characteristic polynomial, or a repeated eigenvalue, an eigenvalue having multiplicity greater than 1, so a non-simple eigenvalue here. So in that case, we have a special name for such a point. So we call points of S such that kappa sub 1 is equal to kappa sub 2 are called umbilics. Okay, and we have a quick characterization of umbilics, just abusing linear algebra here in a second. So note, at an umbilic, at an umbilic point, the Weingarten map applied to T1 is kappa sub 1 T1. The Weingarten map T2 is kappa sub 2 of T2. But kappa sub 1 and kappa sub 2 are actually the same thing. So this implies that W of T is equal to kappa of T if T is any linear combination of T1 and T2. But I mean, T1 and T2 form a basis, right, for the tangent plane there. And so what does this mean? Thus, we have the characterization. Point P is an umbilic point if and only if the Weingarten map is a scalar multiple of the identity. Okay. I.e., I mean, another thing this says immediately is that every tangent vector is principal. Okay. Now, before this lecture is up, I will mention something special about umbilic points. As I promised before, there's an open problem that is extremely simple to state for umbilic points, but is very, very hard to prove. And the reason I say it's very, very hard to prove is that it is still an open problem, right? It has been open for about 100 years, as explicitly stated. So it's definitely tough. Okay. Now, on the other hand, if P is not umbilic, then the principal vectors are guaranteed to be orthogonal. So then the principal vectors are guaranteed to be orthogonal. So they're guaranteed to be perpendicular. Okay. Thus, whether or not P is umbilic, we can always find two orthogonal principal vectors. Okay. And so a corollary of all of this stuff is if I have a point in S, there exists an orthonormal basis of the tangent plane TPS consisting of principal vectors. Okay. And this allows us to state the very important fact, and is kind of the thing that ties together what it is I'm trying to do with these quantities, as the following. So if kappa sub 1 and kappa sub 2 are principal curvatures of a surface, then the mean and Gaussian curvatures are given as follows. The mean curvature is the average of the principal curvatures, and the Gaussian curvature is the product of the principal curvatures. Now, if you remembered your linear algebra, you'd have probably seen this almost immediately here. So the second we have this eigenvalue decomposition, or this diagonalization of W, we can use the basis. So can use basis where in the basis that we got from the previous corollary, we could just set it up so that the matrix for the Weingarten map is exactly this diagonalized matrix containing the eigenvalues, which are these principal curvatures, right? So there you go. Right, we can use any basis we want to here. So why not use this one, where the Weingarten map's diagonalized? So we use that one, there we go. There's our principal curvatures. Of course, the mean curvature was defined as 1/2 the trace. Boom. This is defined as the determinant. The Gaussian curvature is the determinant. There it is. Okay. All right. So this is an extremely nice characterization of these two notions of curvature we have. Okay. For the Gaussian curvature especially, this already you're thinking kind of intuitively about surfaces that you know. And the Gaussian curvature, for instance, of the cylinder being 0, despite in your head you're thinking, well, like the cylinder is curved in some way, right? So a cylinder has some kind of curvature, right? But not, it is still, as we computed its Gaussian curvature was 0 at all points. And so what's going on there? Well, this is telling you kind of what's going on there. We're going to explicitly compute this, but the idea is that in one of the directions, the principal curvature is 0 for the cylinder, and in the other direction, the Gaussian curvature is non-zero, but it doesn't matter because it's getting multiplied by 0. So we can see that explicitly here, right? If I wrap up my paper, you can see that in this direction, the principal curvature is going to be 0. In this direction, it's not. It's going to be some non-zero thing. But it ultimately is not going to matter because in the Gaussian curvature, I'm multiplying that non-zero thing by 0. Okay, and so that is our intuitive understanding for why the Gaussian curvature of a cylinder is 0. Okay. All right. So next, I wanted to kind of briefly take us back with Euler's theorem. This is going to relate the normal curvature of a curve on a surface with the principal curvatures. Okay, so this is a really, really nice way that ties up everything kind of that we talked about when we talked about curvatures of curves on surfaces. All right, so let gamma be a curve. We can, of course, assume that this is unit speed curve, but let's say it's just a curve on oriented surface S, and let kappa sub 1 and kappa sub 2 be the principal curvatures so let these be the principal curvatures of, we'll say we're dealing with surface patch sigma with non-zero principal vectors. Say t sub 1 and t sub 2. Then the normal curvature of gamma. Remember, we had two curvatures associated with curve on surface. We had normal curvature and geodesic curvature. Then the normal curvature of gamma is kappa sub n, which is actually kappa sub 1 cosine squared theta plus kappa sub 2 sine squared theta, where theta is the oriented angle t sub 1 gamma dot. So what do I mean by that? Well, locally in our tangent plane, we have orthogonal basis vectors t1, t2, our principal vectors. Gamma dot is a tangent vector in this tangent plane. There it is. The oriented angle t sub 1, gamma dot means measured from the positive t sub 1 axis here. So here's theta. Okay. And this is, yeah. We have this picture here. Okay. All right. And so the normal curvature can be written in this form involving the principal curvatures. Well, this is actually not too difficult to show because most of this is actually taken care of by our careful setup. Right? And so what do we have? We have a point in S. We have kappa 1, kappa 2, t sub 1, t sub 2 as usual. Okay, so we have principal curvatures, principal vectors associated to them. Okay, by our previous corollary, we know that t sub 1, t sub 2 is an orthonormal basis, ONB, of the tangent plane at P. Okay, whether P is an umbilic or not, we can always do that. We can always find two orthonormal principal vectors. Okay, can assume that, say, the oriented angle from t sub 1 to t sub 2 is pi over 2. If it's not, that is, it's plus pi over 2. If not, just replace t sub 2 with minus t sub 2. It's fine. If not, replace t sub 2 with minus t sub 2. We'll put you there. So I want this to be plus pi over 2 rather than minus pi over 2. Okay, so, all right, then gamma dot, of course, lies on unit circle in the t sub 1, t sub 2 plane. So it is cosine theta, t sub 1, where theta is exactly this angle, plus sine theta, t sub 2. This just comes from the fact that it is a tangent vector, and these form an orthonormal basis for the tangent plane. So that's why I can do this. Now, we had a previous proposition in Chapter 7 when we first met normal curvature that allows us to compute the normal curvature as the second fundamental form of gamma dot with itself. Okay, so this is by proposition. So by proposition, this is from, this is 7.3.5. We know that the normal curvature is the second fundamental form of gamma dot paired with itself. Okay, but then what is this, given what form gamma dot we just said is? This is actually cosine squared theta times it's t sub 1 paired with itself in the second fundamental form, plus 2 sine theta cosine theta, t sub 1 paired with t sub 2, plus sine squared theta of t sub 2 paired with itself. Okay. So this is just me using this fact and the fact that this thing is, the second fundamental form is linear. So then for I and j equal to 1 and 2, what do I have here? If I pair these vectors t sub I and t sub j together, what do I get? Well, by definition of second fundamental form in terms of the Weingarten map, this is W of t sub I, paired with t sub j in the first fundamental form. But of course, the Weingarten map is kappa sub I, t sub I, paired with t sub j here. Well, what is this? If I and j aren't equal, these things are orthogonal. If they are equal, then what I get, since they're unit vectors, I just get kappa sub I. So this is equal to kappa sub I if I is equal to j, and 0 if I is not equal to j. And so what do we have here? We have that the normal curvature is cosine squared theta times kappa sub 1. This becomes 0, and this becomes kappa sub 2, which is exactly the statement of Euler's theorem. All right, there it is. So that does it. Okay. Now, Euler's theorem is nice on its own, but it's going to immediately allow me to say something extremely nice conceptually about the principal curvatures, and that's that the principal curvatures, what they are the max and min values of the normal curvature of all curves on the surface passing through that point. Okay, so I have the following extremely nice fact. Maybe I'll put triple star just for its niceness. Okay, the principal curvatures kappa sub 1 and kappa sub 2 are the max and min values of the normal curvature of all curves on the surface that pass through the point. The point in question. Okay. Moreover, the principal vectors are the tangent vectors of the curves giving these max and min values. So moreover, the principal vectors are the tangent vectors of curves giving those max and min values. Okay. So let's do a quick proof of this. Okay, so suppose for a second that kappa sub 1 is not equal to kappa sub 2. Then without loss of generality, we can assume, say, that kappa sub 1 is greater than kappa sub 2. Okay, we don't have to do that, but we can. So let's assume that that's the case we're in. All right, let kappa sub n be, say, the normal curvature of some gamma. So let this be the normal curvature of some gamma on S. Then, by Euler's theorem, this normal curvature is kappa sub 1 cosine squared theta plus kappa sub 2 sine squared theta, which I can rewrite. So saying cosine squared is 1 minus sine squared, I can rewrite this as kappa sub 1 minus kappa sub 1, kappa sub 1 minus kappa sub 2 times sine squared theta. And so kappa sub n, the normal curvature, is kappa sub 1 minus kappa sub 1 minus kappa sub 2 sine squared. This is, if I assume that kappa sub 1 is greater than kappa sub 2, so this is positive, now that this is non-negative, right? Then what does this say? This says that kappa sub n is kappa sub 1 minus some non-negative stuff. So this means that kappa sub n is less than or equal to kappa sub 1 with equality if and only if theta is equal to 0 or pi, i.e. If and only if gamma dot is parallel to t sub 1. Okay. And similarly, I can say that kappa sub n is greater than or equal to kappa sub 2 with equality if and only if gamma dot is parallel to t sub 2. We have one thing we didn't consider, which is when these principal curvatures are equal, so at an umbilic point. So if kappa sub 1 is equal to kappa sub 2, then kappa sub n is equal to kappa sub 1 by Euler's formula, for instance, or Euler's theorem. And so I also know that every tangent vector is a principal vector, so that's fine. And every tangent vector is a principal vector. So then you take the tangent vector to any curve passing through P, and it is a principal vector. So this statement that the principal vectors correspond to tangent vectors for curves achieving the max or the min, that's easily seen to be true in this case. All right. Okay, so those are some very, very nice conceptual properties of the principal curvatures. But now I actually want to compute them. So now I actually want to compute kappa sub 1 and kappa sub 2. So how do I do that? Well, first of all, let's let sigma be our surface patch as usual. We want our first fundamental form to be the same as normal, e du squared, and so on. And we want the second fundamental form also as normal. This is L du squared, and so on. Okay, what's the matrix of the Weingarten map? So matrix of the Weingarten map is, in general, right, we saw when we first computed with this, this was like this matrix script f inverse times script f sub 1 inverse times script f sub 2. Thus, kappa sub 1 and kappa sub 2 are roots of the characteristic polynomial, which for this matrix is going to be the determinant of script f sub 1 inverse script f sub 2 minus kappa times the identity, right, is equal to 0. So it's roots of this polynomial. Okay. And furthermore, i.e., a vector, if we say t, which is written as like Cassi, I don't know why he chooses Cassi here. So Cassi sigma u plus eta sigma v is a principal vector. So this is a principal vector if we have that script f sub 1 inverse script f sub 2 minus kappa times the identity times vector Cassi eta is equal to 0, 0. All right. So let's write this in a slightly better form. So writing script f sub 1 inverse times script f sub 2 minus kappa times the identity. I can rewrite this slightly as script f sub 1 times quantity script f sub 2 minus kappa script f sub 1. What do I get here? Well, I get the following proposition. So the principal curvatures kappa sub 1 and kappa sub 2 are roots of the determinant L minus kappa E M minus kappa F M minus kappa F and N minus kappa G. This determinant is equal to 0. So if I can find roots of that expression, I have found kappa sub 1 and kappa sub 2. And principal vectors corresponding to principal curvatures are exactly the tangent vectors you expect. And principal vectors are eigenvectors associated to them. Okay, meaning that if I actually write out that whole expression, right, this means that the matrix L minus kappa E, M minus kappa F, M minus kappa F, N minus kappa G times, say, eta, or sorry, Cassi eta is equal to 0, 0. That's what is meant here if I have, say, a vector Cassi sigma u plus eta sigma v. Yeah. All right. And so this is the main way we compute principal curvatures. All right. Okay. Now, let's do some examples here. So let's do the sphere. So let's remind ourselves we have E is 1, F is 0, G is cosine squared theta. Okay. L is 1, M is 0, N is cosine squared theta. Okay. So principal curvatures are roots. So these are roots of 1 minus kappa, 0, 0, and this last one is cosine squared theta minus kappa cosine squared theta is equal to 0. So what do I get? I get kappa is equal to 1. This is a repeated root. This is a repeated root. And what does this tell me? This is a repeated root everywhere on the sphere, right? So every point of sphere is umbilic point, for instance, right? And every tangent vector is principal. So every point is umbilic. Well, that's a very special thing. As we'll see, it's an extremely special thing, and that's not going to come up too often. Let's do another example. So our favorite example that kind of encapsulates everything that kind of intuitively is going on with principal curvature is, well, I said cylindrical, I meant cylinder. Yeah, so this is a cylinder, just normal cylinder. So let's have surface patch. Sigma VV is cosine V sine VU. So cosine V sine VU. Okay. All right. So if I compute EFG, so E is 1, F is 0, G is 1, L is 0, M is 0, N is 1. Okay. So we're looking at roots of the determinant of 0 minus kappa, 0, 0, and 1 minus kappa is equal to 0. Well, what does that give me? It gives me two principal curvatures, 0 and 1. Okay. So any say t sub 1 corresponding to kappa sub 1, which is, I'll call 1, satisfies minus 1, 0, 0, 0 times, say, c eta is equal to 0, 0. So t sub 1 is a multiple of sigma sub v, which is minus sine v, cosine v, 0. And any t sub 2 corresponding to kappa sub 2, which is 0, is a multiple of sigma sub u, which is 0, 0, 1. Hey. So this exactly characterizes our cylinder perfectly, right? So the t sub 1 is going to be a multiple of sigma sub v, which in this way that I folded it up here would be going down this way. And t sub 2 is going to be some multiple of sigma sub u, which is 0, 0, 1, which is pointing this way for us in this picture, okay, with how the cylinder's wrapped up. So this exactly explains what's going on there in terms of these principal curvatures. Now, I wanted to note a couple of things here. So note every point of the sphere is umbilic. Same is true for a plane. Now we have the following proposition. that is going to say that basically this characterizes what kind of surface you have. If you have a surface that's nothing but umbilicus, it's either a sphere or plane. So let S be a connected surface of which every point is an umbilic. Then S is an open subset of a plane or a sphere. This is our analog of this fact that said, before we had a plane curve with constant curvature as part of a circle. This is kind of an analog to surfaces for that. Okay, the proof of this is on page 192. Okay, and so there's not many surfaces that all of whose points are umbilics. So that's a very special thing. Now you might ask yourself, like, what's an example of a surface that doesn't have hardly any umbilics? All right, so here's an example. Say an ellipsoid. So an ellipsoid has two umbilics. Okay. Maybe like here and here. You might say, wait a minute, this is symmetric in some way. Why are like these down here not umbilics? So I may have you do a computation for an ellipsoid to show the umbilic points. It turns out that this has exactly two umbilic points. So like I said, maybe I'll have you all do a computation involving those soon. This has exactly two umbilic points. Okay, so we've got surfaces that have infinitely many umbilic points. Every single point's an umbilic. We have surfaces that have two umbilics. And the question is, can I have a surface that has none? So the answer to that is no, but there's some machinery that's needed to say that. So one, I restrict my attention to, say, closed convex surfaces for now. So we'll say surfaces that topologically are a sphere. Okay. And for that, I have the Carat-Theodori conjecture. Now I believe this was stated in 1922. This is still very much an open problem. So this says that any closed convex surface S must have at least two umbilic points. So as I've said, it has been shown since that any closed convex surface has to have at least one. We have an example of the ellipsoid that has exactly two. And so in some sense, the Carat-Theodori conjecture is saying that the ellipsoid is the minimum number of umbilic points you can have. It's kind of the min case, whereas the sphere is the maximum. Okay, every point's an umbilic. Okay, so this is a very simple to state. You now know every single quantity that I have defined here. You are 100% aware of the definition. You know exactly what those things mean. And here is an open problem. Okay, like I said, that is still very much open. In fact, I'm not even sure. I think even resolving this in An easier case is something that hasn't quite been. So I know that there was an easier case that was done by a guy in the 40s. That proof is fine, but it wasn't fully realized that that proof was fine, I think, all the way until like 1980 or something. Um, I would have to go back and look through the history of this, but this is still an open problem. This has not been solved. There was supposedly a proof announced for this like 13 years ago, but that has not been published yet. So this is still very much an open problem. Okay, if you are interested in such things, this is a prime example. I think actually, famous mathematician. I can't remember if it was Hardy or Littlewood, said this is a great example of a problem that is very easy to state but very hard to prove. So anyway, interesting. This is an interesting problem to consider. All right. So my main thing I want to do now, and then I'll be done, is to say how these curvatures tell the shape of the surface. So how can kappa sub 1 and kappa sub 2 tell me the shape of S? Okay. Well, let's assume P is the origin. Let's assume that the tangent plane is the xy plane. We'll set ourselves up for success in that way. Kappa sub 1, kappa sub 2, principal curvatures. We then have vectors t sub 1, t sub 2, and n, which form an orthonormal frame, or orthonormal basis for R3, actually. Okay. So let's let sigma be our surface patch. We'll say sigma of 0, 0 is 0. Okay. Then for all x and y in R, there exists unique S and T in R such that we can say x, y, 0 can be written S sigma u plus T sigma v. This is because these are an orthogonal, they're an orthonormal basis, right? These derivatives are evaluated at 0, 0. So I won't write that from now on, but just to keep in mind, those are evaluated at 0, 0. Okay. By Taylor's theorem, sigma of ST can be written as sigma of 0, 0 plus S sigma u plus T sigma v. That's the first order term. Plus 1/2 times I have our second order term, which I can write as like S squared sigma uu plus 2st sigma uv plus t squared sigma vv, and higher order terms, whatever. Right? Okay, if S and T are small, then sigma of S T can be thought of as x, y, z, where z is equal to this amount of bend, so 1/2 S squared sigma uu plus 2st sigma uv plus T squared sigma vv, which of course is, I can rewrite in terms of, dotted with, say, the standard normal, which I can rewrite in terms of the second fundamental form. This is 1/2 times L s squared plus 2m st plus n t squared is what I get there. Okay, this is approximately, right? This is approximately the case. So this is when s and t are small. I'm evaluating second fundamental form terms here this is at the origin, right? So this is my second fundamental form near the origin. Okay. Well, note if my vector t is s sigma u plus t sigma v, right, then I know that this L s squared plus 2m st plus nt squared, this comes from the second fundamental form. So really, this is the second fundamental form of t paired with itself. Right? But then the definition of that, of course, was the Weingarten map of t paired with t. This is the first fundamental form. But the Weingarten map at t, for a principal vector, of course, we know the special form it takes because these are the principal curvatures. And so, now, if I take, say, my vector to be in terms of, so my generic vector can be written in terms of this basis t1 and t2, so x t1 plus y t2 here. So then the Weingarten map of t, because it's linear, this is x times the Weingarten map of t1 plus y times the Weingarten map of t2, which is kappa sub 1 x times t1, because the Weingarten map of t1 is kappa sub 1 t1, so it's kappa sub 1 x. This looks like kappa sub 1 times, or cross t sub 1. That's an x. Plus kappa sub 2 y of t2. Okay. So, in other words, rewriting this, this is kappa sub 1 x, kappa sub 2 y, 0. So that is what my Weingarten map applied to a generic vector t is, which of course can be written as a linear combination here of my principal vectors t1 and t2. Thus, L s squared plus 2m st plus n t squared is equal to, this is kappa sub 1 x, kappa sub 2 y, 0, dotted with t, which is x, y, 0. Where does this come from? This comes from this statement that I wrote here. Okay, so this here, I'll write it again here. Ls squared plus 2 mst plus nt squared. This was t paired with itself, which is the first fundamental form of the Weingarten map of t paired with t. Okay, so we saw that the Weingarten map of t can be written as, in terms of principal curvatures, kappa sub 1x, kappa sub 2y, 0. This is all near the origin, right? So this is very near the origin is where we get this expression. And so what this is kappa sub 1 x squared plus kappa sub 2 y squared. What is the point? Thus, near P, S is approximated by the quadric surface z is equal to 1/2 times kappa sub 1 x squared plus kappa sub 2 y squared. This is a very, very cool fact. Okay. Yeah, this is a very, very neat fact. And this fact is extremely important because it actually allows you to classify points on a surface, or rather neighborhoods on a surface, because this is all happening, of course, near P. And so there are 4 cases we can talk about. This splits into a surface into types of points where near those points the surface is looking a certain way. Approximated by a quadric surface, we're very familiar with what these things look like. Okay. And so this is what I will talk about very briefly when I get back, or when we have class on Monday. I will finish up this